Assalamualaikum. My name is IRDINA binti SUHAIRI. Right now, me and my group will be presenting Discrete Structure project with topic of logic. Our group consists of 3 members. Laura will be presenting negation, conjunction, and demonstration. Hidayah will be presenting disjunction, exclusive, and conclusion. Lastly, I will be presenting introduction, implication, and biconditional. Today, I will be introducing logic operators and why they are important in mathematics and computer science. Logical operators are symbols or words that help us work with statements and determine whether they are true or false. They are widely used in programming, digital system, and logical reasoning because they allow us to combine or modify information and make decisions based on the condition. There are several basic logic operators. The first one is NOT, which is simply reverse the truth value or of the statement. If the statement is true, applying NOT makes it false. Next is AND, which is only true when both statements being compared are true. OR is another common operator and it is true when at least one of the statements is true. XOR or exclusive OR is slightly different because it is true when only exactly one statement is true, but not both. We also have if-then, which show a conditional relationship. It means that if only one statement happened, then another statement follow. Finally, if is true when both statements have the same truth value, meaning they are either both true or both false. Logic operators are important because they are used in programming, digital circuit, security system, and artificial intelligence. They provide structured way to evaluate information, make decisions, and solve problems efficiently. In conclusion, logic operators form a foundation of logical reasoning and many modern computer systems.
My name is PUTRI BATRISYIA binti S.ROAIDI. Now, I will explain the NOT operator, also known as negation. The NOT operator reverses the truth table of a statement. If a statement is true, NOT makes it false. If a statement is false, NOT makes it true. As shown in the truth table, when A is true, NOT A is false. When A is false, NOT A is true. The NOT operation is represented by a NOT gate. The output is always the opposite of the input. For example, if the input is 1, the output becomes 0. Let's look at an example. If statement A is "it is raining," then NOT A means it is not raining. We can also see NOT being used in real life. For example, a car alarm activates when the door is not closed, and an automatic room light turns on when the room is not empty. In conclusion, the NOT operator simply inverts the statement and is one of the basic building blocks of logic and digital systems. Next, I will explain the AND operator, also known as conjunction. The AND operator combines two statements, A and B. The result is true only when both A and B are true. If either one or both statements are false, the result will be false. As shown in the truth table, there is only one situation where A and B is true, which is when A is true and B is true. All other combinations produce a false result. In digital logic, the AND operation is represented by an AND gate. The output is 1 or true only when both inputs are 1. For example, let A be the light switch is on and B the bulb is not broken. The light will turn on only if both conditions are true. A real-world example is a security system. The alarm activates only when the door is open and the correct code is not entered. In conclusion, the AND operator is more restrictive because the result is true only when all conditions are true.
My name is HIDAYAH IZZATI binti HYRIL ANUAR. This slide explains the OR logical operator, also known as disjunction. OR returns true when at least one of the input is true. It only returns false when both inputs are false. Looking at the truth table, we can see that whenever A or B is true, the output is true. The OR gate symbol shown on the right is commonly used in digital circuit and computer system. For a real-world situation, consider an automatic street light. The light turns on when it is dark or when motion is detected. As long as one of these conditions is met, the light will switch on. A simple example is, "It is raining" or "I have an umbrella." The statement is true if either condition is true or if both are true. This slide explains the exclusive OR XOR logical operator. XOR is different from the normal OR operator because it produces a true output only when exactly one input is true. Looking at the truth table, when A and B are different, such as true-false or false-true, the output is true. However, when both inputs are the same, either both true or both false, the output becomes false. On the right, we can see the XOR gate symbol used in digital electronic and computer system. For the real-world situation, consider a two-way switch light control. The light turns on only when one switch is on. If both switches are on or both are off, the light remains off. This follows XOR logic because the input must be different. For the example, let A represent it is a weekday and B represent I have free time. The statement A XOR B means either it is a weekday or I have free time, but not both at the same time. Therefore, XOR is true when only one condition is true, and false when both conditions are true or both are false.
In this slide, I will explain the logic operator called implication, which is represented by symbol arrow OR. Implication means if A, then B, where A is called the conditional and B is the result. In a simple term, it states that whenever A happens, B should happen. One important rule about implication is that it is true in almost every situation except one. It becomes false only when A is true but B is false. In other words, a condition happened but the expected result does not. Looking at the truth table, we can see that when A is false, the implication is always considered true, regardless of whether B is true or false. It is also true when both A and B are true. The only false case occurs when A is true and B is false. A real-life example is, if it's raining, then the ground is wet. If it's raining, then the ground is wet. The statement is true. However, if it is raining but the ground is not wet, the statement becomes false because the expected result did not occur. To summarize, the implication is a logic statement that connects the condition to a result. The key thing is to remember that an implication is false when the condition is true and the result is false. In other cases, it is considered true. Next, I will explain about the biconditional operator, which is represented by a symbol, the arrow both sides, and the read as if and only if. The biconditional statement, it is true when both statements have the same exact truth value. That means that if both A and B are false, the result is also true. Because if one statement is true and the other is false, the biconditional statement becomes false. Looking at the truth table, we can clearly see that the output are true when the input match. When A and B are different, the output is false. Because of this, the biconditional operator is often used to show two-way relationship where each statement depends on one another. A simple real-life example is wearing a helmet and wearing a seatbelt. The statement says, I wear a helmet if and only if I wear a seatbelt. This statement is true when I wear both safety items or when I wear neither of them. However, it becomes false when I wear only one and not the other. In conclusion, the biconditional operator helps us compare two statements and check whether they have the same true value, and the key idea is to remember that the result is true when both inputs are the same and false when they are different.
In conclusion, logical operators such as NOT, AND, OR, XOR, if then, and if and only if help us evaluate statements and make logical decisions. These concepts are important because they form the foundation of the computer programming, digital circuit, security system, artificial intelligence, and many other technologies. By using truth tables and logic gates, complex problems can be represented and solved systematically. Therefore, understanding logic is essential not only in mathematics and computer science, but also in many real-world applications. Thank you.
Next, we will move on to the demonstration part of our MATLAB project. In this program, we apply two important programming concepts, which are repetition and selection. First, repetition is implemented using while loops and for loops. The for loops are used to automatically generate the truth tables for each logic operation by testing all possible inputs combinations. For example, for our project, is basically on this part. Next, the while loops allows the user to repeatedly test different inputs and return to the main menu without starting the program. So basically for our project, for that part is this part, where we ask the user to key in the input as a variable of choice. So when choice is Y, it will basically go to the main menu and output the main menu. So technically, it returns to the main menu without starting the program. Next, selection is implemented using switch case statements and if-else statements. The switch case structure allows user to select different logic operations such as AND, OR, XOR, implication, and biconditional. For example, for our MATLAB, for each logic operation, we relate them with the real-life situation. For example, the switch case is switch variable option, and the case 1 is AND, relate with smart home security system. The second one is case 2, which is OR, relate with scholarship eligibility checker. The third one, which is case 3, XOR, relate with smart classroom attendance system. The fourth one, which is case 4, for implication, this is related with academic performance evaluation system. And the last one, which is case 5, biconditional, it is related with student result evaluation system. Meanwhile, the if-else statements are used to evaluate the user inputs and display the appropriate output based on the logic rules. For example, when we look at the end, we have the if-else. So basically, we display the appropriate output based on the logic rules that the user has given, which is the input. For the output of our MATLAB project, first thing first, it will display the main menu, which is this one, and the user can select which one they want to go through first. There's 5 options here. And for example, if I want to go for an operation, then I will enter 1. And then it will display the real life situation for the N, which is smart home security system. And this is the truth table for N. And then it will have a system test. So the user can test whether the N operation is correct or not. So for example, if I say correct, and I'll say 1. And I say fingerprint verify, I'll say 0. So the output access denied, which means 0, DORI means log, and security alert activated. And it's going to ask again whether we want to test the N operation again. So when we say yes, it will test again. So now we're going to do the access 1. So we're going to pass it correct, is yes, so it's going to be 1. Fingerprint verified, 1. And the output is expected, it's supposed to be access granted since it's 1 here. And door open successfully and welcome home. Now, if I want to go to the main menu, so we're gonna not test the end operation again, and we're going to return to the main menu, so I'm gonna say yes. So now it goes back to the main menu, and I want to do for OR operation. So now the operation is the same thing as AND operation, except the real life situation is scholarship eligibility checker, and it's going to display the OR truth table. So now high CGPA, I'm going to do 1. And no family income, no, so it's going to be 0. So expected it should be 1 for scholarship. So it is correct, scholarship approved, and approved due to high GPA. It's OR operation again. I'm going to say no, and goes to the main menu to test other logic gate operation. So we're going to test XOR now, which is number 3. And for the XOR, it is a smart classroom attendance system. So this is the display for the truth table of XOR. And we're going to go with this one, where physical is 1, online is 1, and attendance is 0. So the outcome should be 0 for the attendance. So physical attendance, yes. Online attendance, yes. So now it is invalid attendance because student cannot attend both modes simultaneously. So are we going to test XOR again? I don't really want to do that, so I'm going to say no. I want to go to the main menu. Next, we will go through for the fourth one, which is the implication. So we're going to enter 4. And it is for academic performance evaluation system. This is the truth table. And now we're going to do the implication test. So for example, if we're going to go with this one. So the assignment should be 1. And then attendance recorded is 0. So condition is violated, which is the expected result because it's 0. And assignment submitted, but attendance not recorded. So I'm not going to test the implication again. I'm going to go to the main menu for the last one, which is the biconditional. Okay, so the biconditional is for the student result evaluation system. This is the truth table. And we're going to test it out for this part. So system mark pass, 0. Lecture mark pass, 0. Both sides agree. So basically the result is true. It's the positive result. So we're going to test the biconditional again. No. Return to main menu, yes. So for extra, when we key in the input, when we do, for example, 2, if it says invalid input, please enter only 0 or 1, or even 0.3, I guess. It will say that again. So basically, you have to enter either 1 or 0. It's very restricted for that. So 1, and then 1. And then we're not going to test it. We're going to terminate the program now. So we're not going to return the main menu. So it's going to be like this. So this is the end of the demonstration. That's all for me. Thank you.